Welcome to Geometric Reasoning. In this video, I'm going to show you how to apply some geometric properties to deduce unknown angle quantities within some diagrams. So over here in A, notice that we've got two parallel lines, and the two parallel lines are intersected by two non-parallel lines, so two arbitrarily placed lines. Now, of these, we're given some known quantities, so this 115 degrees and this 75 degrees. And then it's asking us to find this unknown value x and this unknown value y. Now, to solve these particular problems, what we need to do is we need to reference our geometric properties that we would have seen in last year, so year 8. Now, the ones in particular for this sort of problem here are the properties involving parallel lines. So what we can see is that we've got a property called corresponding angles, alternate angles, and cointerior angles. And these three properties here allow us to deduce, by geometric reasoning, the angles subtended by these arbitrarily placed lines here. So say, for example, if we're trying to find the value of x, we can easily deduce the value of x by looking at, say, the corresponding angles or looking at the cointerior angles. Now, what we can see is this 115 degrees here. What we can see is that because this is 115 degrees, by looking at the alternate angles, what we can see is that because this is 115, what we expect is over here, this will also be 115 degrees. And then looking at the cointerior or allied angles, we can see that x plus this value here, so 115, must sum to equal 180 degrees. So therefore we can build an equation that describes the value of x. So what we can write is x plus 115 degrees is equal to 180 degrees. And we know that by cointerior angles. Now, simply solving for the value of x, we get x is equal to 180 degrees. Take 115. And therefore, that's going to come out to be, x will be equal to 65 degrees. So nothing too flash there. Now the next one we can look at is the value of y here. So again, looking at our geometric angle or our parallel line properties, what we can see is that we're looking at the property for the corresponding angles here. So y and 75 degrees, these two angles subtended here, they're corresponding angles. So we can simply go straight in for the kill and we can say y is equal to 75 degrees. And reason being for that is that they're corresponding angles. So nothing too flashy. All we're simply doing is we have a look at the diagram and we try and match the diagram to these geometric patterns that we can see over here. And if we can see the pattern, we just state it and we use it, and therefore we know what the angle is going to be. Alright, let's go down to B. I should say let's bring B up. We've got this diagram over here. We've got M, we've got N, and we've got R. Now we ask ourselves which is going to be the easiest of these to deduce. And simply by looking at this, I would assert that the M is probably the easiest to do. Reason being is that if we look at our cointerior angles, what we're going to see is that, again, this M and this 70, they're going to need to sum up to equal 180 degrees because they're on the same line and it dissects this line here. So there must be, between these two lines, it must be 180 degrees. So we can write the equation M plus 70 degrees is therefore equal to 180 degrees. And of course that is cointerior. Notice how I'm writing the geometric property next to the line where I'm using it. Reason being is that we have to use deductive reasoning, or geometric reasoning I should say, to get to our final answer. It's no good to simply state what we see, but rather we also have to state what we see and write down the geometric property we're using. Now, rearranging, we get 180 take 70, and therefore our value for m is equal to 110 degrees. So this one is now done. That's 110 right there. Now we have to look what would be the next easiest one to deduce. And simply looking at this, the next easiest one, in my opinion, to deduce would be this value for n here. So look at the relationship. We've got these two parallel lines here, and this common line going through here, and we've got m and n. They're sort of in the same position. So what we actually see is that the value of n is in fact equal to the value of m, and the property that I'm using to justify that is the corresponding angles. So you've got these two parallel lines here, and look at the blue here and here. Well, we can see it's the same pattern going on. So n and m are equal by corresponding angles. Therefore, the value of n is also equal to 110 degrees. Too easy. Now, final value on our list. We've got the value for r here. Now, we need to have a look at it. What properties can we use to deduce the value of r? So we've got these two parallel lines. One is here and one is here. Then we've got this arbitrary line that cuts through both these parallel lines. Now on this line here, the arbitrary one, we've got an 80 degrees and then we've got the r. So let's have a look at our properties, geometric properties, and see if anyone can help us describe the relationship between r and this 80 degrees here. Now looking at the arrangement of r and 80, we have a similar arrangement in terms of alternate angles here. So look at the purple, and then the purple flipping over to the other side, so opposite. So what we've got going here is r and 80, they're in a relationship of alternate angles. So what we can see is the value of r is in fact equal to 80 degrees, and it's equal to 80 degrees for alternate angles. So nothing too tricky there. So that is B complete. Now let's go down and we'll grab C and we'll gearing it up so it's just underneath B. Alright, now looking at C, we've got unknown quantities for A, C, B, and D. Now we ask ourselves, how can we get involved in this question? What would be the easiest one to do? And looking at this, we've got this common line here, it's a straight line, and then it's broken up like so. So I've got 140 and A. Now looking at our angles here, we can use our cointerior angles to help us solve this problem. So notice that A and 140 have to sum to equal 180 degrees. So A plus 140 has to equal 180 degrees, and that is through cointerior. So that's A equals 140 or 180 take 140, and therefore A is equal to 40 degrees. Nothing too tricky there. Now next one we want to look at is, we'll go C and this right angle. Now one of the proofs that I haven't shown you is it's not going to be, or the way in which we're going to solve for C, it's not going to be through these parallel lines, but rather it's going to be through something different. It's going to be through, where are we? Here we go. So it's going to be through our pairs of angles. Now looking at this, the pairs of angles that we're interested in is the vertically opposite. So you've got two lines that cut each other, so two straight lines that cut each other, and the angles that are opposite one another, they're actually equal to one another. So what we can say is that the value of C is therefore equal to 90 degrees, because that's what this little box here tells us. It's a right angle, and they are equal, C is equal to 90 degrees because of the property of being vertically opposite. Again, nothing too tricky. Now let's turn our eyes to B. Now with B, we're dealing with, over here we've got a parallel line, and over here we've got its complementary parallel line, done by this arbitrary straight line like so. So what we need to do is we need to look at our properties, geometric properties involving the parallel lines. So we need to look, is there any geometric property that will help us deduce this here? Now the property we can look at to help us understand this particular problem here of what B is we need to look at our alternate angles. So look at this orange here and this orange here. So let's go this. So we're going to get this 140 and what would be formed by that angle in there. And then we'll go this green color here, put it over B. What you can see is that based on the geometry layer or geometric layer, we've got this alternate angles situation going on here. So therefore we can deduce from alternate angles, B is therefore equal to A, and that is through alternate angles. And because B is in fact equal to A, what we find is that therefore B is equal to 40 degrees, like so. Now, final one we need to look at is the value for D here. Now notice, look at the arrangement of B, C, and D. We've got B and C as the interiors of a triangle. So I'll clean this up. Okay, so we've got B and C as the interiors of this triangle we see in here. And then we've got D on the exterior of the triangle. Now, looking at this, what we know is that the angles in a triangle sum to 180 degrees, like so. So therefore what we'd expect is that B plus C, and we'll call this one in here E, must equal 180. So B plus C plus E must equal 180. Now look at the relationship between E and D. So if we're looking at E and D, what we find is that E plus D must equal 180 degrees as well. So because of this reasoning here, what we can say is that B plus C plus E is equal to E plus D. And notice we've got E on both sides of the equation, so those two can go, and therefore we have D is equal to B plus C, and we want to find D, so we can say it's equal to B plus C. Now, what we've got here is something called the exterior angles of a triangle proof. So, exterior angles of a triangle. And this is our proof to tell us what the value of D is going to be, because remember, we've already deduced the values for B and for C. So simply putting in the values for B, that was 40, and C was 90, now both in degrees, what we find is that D is therefore equal to 130 degrees. So that's probably the trickiest of all of the examples we do. Now, we don't have to write all of this when we're going for this particular rule. All we need to do is, let's change that to the color. So we can skip all of this step in here, and we can go down to here, D equals B plus C, because exterior angles of a triangle, and then we therefore rearrange and solve for D to equal 130. So nothing to it.